Welcome to the 13th chapter of the Crystal Clear Electronics 2 curriculum. Today's topic will be the classification of sensors, understanding their operation, and their applications. I'm Erőd Kovács, and I recently graduated from the Bolyai High School in Szombathely, Hungary. I'll be assisted by Sarolta Terplán, a current student from the Bolyai High School. Can you tell us a few words about yourself?
Hi, I'm Sarolta Terplán, currently an 11th grade student at the Bolyai Gymnasium. I was introduced to the Crystal Clear Electronics curriculum 2 years ago when I started visiting the Crystal Clear study group in my school. I see my future as an engineer, that is why electronics and programming are important to me. Our current topic on sensors has already been covered in Crystal Clear Electronics 1, Chapter 23. For those who haven't read the written material or watched the video, I would highly recommend it now. Erőd, how does this chapter differ from CCE 1, Chapter 23?
Chapter 23 covers the basics, such as the introduction to serial and parallel communication and the most common terms used in the subject, but is not nearly as detailed as these videos. This chapter is also longer. It has more video parts than usual due to the diversity of sensors.
Sensors are converters between the analog and the digital worlds.
This means that they establish a connection between the circuit and its environment, converting physical quantities into signals that the circuit can interpret. Nothing proves this better than the fact that there are plenty of them in the average household, as most electronic devices have at least one. What they exactly do and how they work will be discussed in the upcoming videos.
They are an integral part of our daily lives because of their wide range of uses. Just to name a few: touchscreen displays, motion sensing lights, or automatic soap dispensers. It is particularly interesting to see sensors with other uses and how they play an important role in other areas, such as in medicine.
In this chapter, you will learn about some of the incredibly diverse usage and the main classification aspects of sensors, as well as gain a clearer picture of how they work. Hopefully, after watching the videos, you will also be able to write a program that will make the different sensors on the panel work.
By the end of the chapter, you will gain some useful practical advice alongside the theoretical knowledge.
The chapter was written by Botond Csató and was revised by Ákos Péter Girgász. I think it is time to take a seat and get started. For a circuit to detect signals from the physical world, it needs a conversion device that can convert these signals into electrical signals that the circuit can interpret. These conversion devices are sensors, which are needed in any circuit that expects some kind of input signal from the outside and are therefore found in the vast majority of electronic devices. Think for a moment about the number of sensors in the phone in your hand. Some of them are, for example, the microphone, touchscreen, camera, accelerometer, gyroscope, light sensor, and GPS receiver. I think it is not necessary to go into the function of the first three. The accelerometer allows the device to detect changes in its speed, and with the gyroscope, the phone can determine the orientation of the display based on which it rotates the displayed content. The light sensor allows the cell phone to adjust the brightness of the display to the environment, or it can even detect when we put it in our pocket. The GPS receiver can also be seen as a kind of sensor, which takes radio frequency signals from satellites orbiting the Earth and, after appropriate signal processing, determines the global coordinates of the device.
In practice, you can also think about sensors as being the sensing elements of circuits. I think it's interesting to consider that the antennas in our electronic devices are also technically sensors. Among other things, this is how you can communicate wirelessly using electromagnetic waves, or how radio telescopes can observe distant stars. But what kind of parts does a sensor contain?
The spirit of the sensor is a direct conversion device that converts a physical signal into an electrical signal that can be interpreted by the processing circuitry. This direct conversion device can be preceded by converters that perform a conversion between different physical signals. As an example, let's think of a two-part chemical sensor, such as the sugar sensor that I also use. The first part of the sensor, the converter, in this case is an enzyme that reacts with the sugar in my body, releasing hydrogen ions. The second part of the sensor is a direct converter, which produces an electrical signal based on the amount of these hydrogen ions. In this example, the first part of the sensor produces ions proportional to the concentration of sugar, and the output of the direct converter is a voltage proportional to the ions.
The sensor mentioned in the example converts ion concentration into an electric signal, but there are also solutions based on, for example, kinetic, magnetic, or thermal energy. It is worth mentioning that reverse energy conversion devices, which convert electrical energy into other types of energy, are called actuators. You can think of actuators as being the hands of the circuit, one of the simplest such devices being the electric motor.
Sensors can be grouped in several ways. The simplest categorization is that there are passive and active sensors. These categories are defined differently by different sources, but we will consistently use the approach which we will discuss now. Active sensors do not require a power supply. The physical signal input generates the electrical signal output. Active sensors include thermocouples, photodiodes, and piezoelectric sensors. Active sensors are also known as generator-type sensors, since a generator is an energy converter that converts mechanical energy into electrical energy and does not necessarily require an electrical power supply for this process. It logically follows that passive sensors require an external power supply to provide the electrical signal output. This category includes, for example, temperature-sensitive resistors, also known as thermistors, whose resistance is related to its temperature. You will learn more about this type of sensor in the following chapter. As you probably know, to calculate the resistance, you need to measure the voltage across the resistor and the current flowing through it, and the electrical resistance is the quotient of these. Consequently, a power supply is needed to measure the temperature of a thermistor. Another name for passive sensors is modulator-type sensors. The name refers to the fact that the input physical signal changes and modulates the electrical signal supplied by the power supply.
Another classification distinguishes between absolute and relative sensors. The output of an absolute sensor is interpreted on an absolute scale. In contrast, the output of a relative sensor carries information in the form of something. In this case, a reference value is needed.
For example, there are absolute temperature sensors that determine the temperature relative to absolute zero, which is 0 Kelvin, for example, using a special property of semiconductors. There are also relative thermometric sensors, such as thermoelectric thermometers, whose output is proportional to the temperature difference between 2 points. Therefore, to determine an unknown temperature, a known reference is required. To mention a simple example, you want to know the absolute temperature of the teacup before you touch it, but you want to know the relative temperature of the liquid and the glass beaker before you pour the liquid into the beaker if you don't want to break it.
You will hear more about temperature sensors in detail later in the videos of this chapter. A third sorting principle is the type of physical signal input. Examples of this are given in the following table.
Physical signs can be divided into several broad categories, and within each of these categories, there can be several or even just one type of physical sign. When measuring, for example, an acoustic signal, the input is almost always sound pressure, but biological signals include blood glucose, oxygen saturation, and many others. I'm not going to read the whole table now. If you're interested, you can stop the video to study these categories.
This will bring us to the end of the first video. We have learned about the definition of sensors, their construction, and their different classifications. In the next 2 videos, we will take a look at common sensor types. We hope you will join us there too. Bye!